Is that alright? Can you hear me at the back yet? Oh, excellent. So, unfortunately, I was asked to shorten my talk, so I decided that I didn't need to motivate multi-photon interference experiments at this workshop, so but that was where I cited all of your work, unfortunately, so you'll have to forgive me for that. So I'm going to focus on a couple of photonic interference experiments that I did at the QT lab while I was there with Andrew White. So I'll get straight into it. Yeah, so it turned out while I was there we were publishing at least one quantum walk experiment per year, but then in 2014 we got hit by the referees, so that was a bad year. But we started off by looking at these single photon quantum walks in space, and we moved on to these integrated circuits where we looked at quantum walks on a circle with periodic boundary conditions. That's the first time actually where us in our lab we did a multi-photon quantum walk. We then used these systems here to investigate topological properties of quantum walks. And finally, a couple of years ago, we did one of the first BosonSampling experiments in a fiber optic network. So today I'm going to talk about two experiments that are essentially related to these two smaller results that are related to these bigger ones. The first one I'm going to talk about is how to characterize a linear optical network just using classical resources alone, and why that's important to do, for example, for boson sampling. And the second half of my talk is going to be on this enhanced quantum transports, or ENAQT. It's believed to be responsible for some quantum effects in biological systems. So this will be part one of my talk. So the people involved in this project are listed here. In particular, I want to point out Robert Fickler, who came over to visit us back in 2012, I think. And this research was funded by the Australian Government and the Centre of Excellences. And the paper I'm talking about here was published, actually that should be 2013, I think. So, as you know, I'm really not going to spend much time talking about boson sampling because Andrew already did it and you've heard enough about it already this week. But essentially, we did our experiment in a 6-mode fibre optic circuit, where that was built up from one non-polarising beam splitter, 3x3 non-polarising beam splitter, and 3 polarising beam splitters on the output. So by encoding polarisation in space, we essentially can go from a 3x3 to a 6-mode linear optical network. The photons are produced by spontaneous parametric down conversion. All my animations are missed. So the way we set up the problem in our experiment was, you've got one quantum computer scientist who has access to quantum resources, and you've got so they're going to actually put single photons into this device and measure the output statistics. The way we did that was using the visibility measure between distinguishable and indistinguishable photons. And then you've got this classical computer scientist who's only allowed to use classical resources. So I guess the way we were looking at it, it's essentially a race. So you give both of them this black box and you say, go away, and whoever gives me the sampling first wins. And of course, Scott Aronson showed that it was the case that a classical computer scientist is not going to win in that case, as the system scales up to 20 or 30 photons. But of course, the classical computer scientist has got to be able to match what the quantum computer scientist can generate with their quantum resources. These are just a few of our results put in for show. But you only want to allow the classical computer scientists to have access to classical resources, so just photodetectors and laser beams, essentially. So that was our motivation for trying to find a classical characterisation technique. So I think we've seen some absolutely fantastic work this week, especially yesterday, some of the speakers talking about these large-scale integrated circuits. And one thing's for sure is that these linear optical networks are getting larger and larger. they're going to eventually become very difficult to characterize. Of course, as you scale up the system, for n qubits you need something like 2 to the power of 4n measurements to do full process tomography, so that's just not feasible. But you don't need full process tomography for a lot of experiments, and boson sampling is one of those. So again, like I was saying earlier, the challenge is essentially to characterize this black box unitary, or unitary in inverted commas, because obviously we know that it's not unitary. There are techniques already out there to do this. In fact, there is already a classical technique to do this. It was published in 2003. But it requires embedding your linear optical network in this huge array of interferometers, which is quite messy and complicated experimentally. The other, there are other quantum methods as well, but this is just the one that I picked just for comparison, published by Lang and O'Brien in 2012, where they show that you can use single photon probe states to characterize the beam splitter network, the phase shifts and the beam splitter ratios. Now, obviously, we looked at this when we started doing boson sampling, but we felt it wasn't really in the flavour of what we wanted to do because it was a little bit circular. You're essentially relying on quantum interference to characterize your device, which you're going to then do quantum interference in. Either way, it requires quantum resources, and that makes it difficult from the get-go. So instead, what we developed was a simple technique that just relies on single and dual mode coherent states, input into your black box unitary, and photo detection at the output where we just measure intensity. So the method works like this. You've got some unitary, which is made up of moduli and phases in each element. What we do to start with is just neglect the phases on the first row and first column. This is equivalent just to transforming your unitary using this diagonal operator here. But importantly, U and U dash here describe the same physical process, and that's the actual physical process that you want to characterize. You can just throw away those phases. So to characterize a module like that is really simple. You just input light into one mode and measure the intensity at the output, and you do that obviously for every mode. To characterize the phases, you just split your input coherent state at the input here. You just input 2 and measure the intensity on each one of these photodiodes as a function of this phase here. Okay. So, as I already said, the first phase is going to be equal to 0. So the second phase is reference to that, and then you can just pick these off one by one as you change which mode you put the second coherent state into. Then you just change the row that you're getting those phases from. So it's really simple. We essentially use the same devices we use for the boson sampling. So it's again this 6-mode linear optical circuit made up of a fibre beam splitter and 3 polarizing fibre beam splitters on the output. This is the operators that you're interested in. And the actual experiment looks like this. So we just use calcite crystals on the input to control calcite crystals and wave plates just to control where the laser modes go. It's all electrically controlled, so you don't have to actually touch anything. You just sort of set it up and it goes automatically. And using a linear actuator on all of the input modes, you can modulate phi, and that's how you get access to the phase information in the network. Obviously, you have to measure these photodiode currents as a function of phi, or as a function of time as you sweep this. So using the oscilloscope to grab all the data.
So you've done it or you propose it?
No, we've done this.
And no local oscillators, just...
No local oscillators, just in this manner, yeah. So, oh, to go through it all again. It's alright. Troublemaker. These are the results. So, yeah, the matrix, what we're happy about is that the matrix we're sampling from was not sparse, so it's, you know, pretty dense. There's lots of elements in there for the photons to interact with, and the phases are given over here. Of course, you know, we didn't expect unitary to be unitary. In fact, I was really pleased about that. It tells me the universe isn't working with me. And our main source of non-unitarity is loss, which is what you'd expect. We just developed a simple method to account for this loss just by introducing these fake beam splitters. These are not real. These are, you know, these are just how to model loss. You can just bring all the loss for each mode into the front here, placing a beam splitter with some reflectivity. So what you would actually like to characterize if you wanted to know everything about this circuit is this larger matrix VM, which again in an ideal universe should actually be unitary. Okay. So yeah, so we can actually characterize the loss as well by measuring the input power and measuring how much power comes on the output, right? So it's pretty straightforward. And that basically ascribes one of these beam splitter reflectivities for each row in this larger matrix. So this is your UN that you've tried to characterize previously, and this larger matrix V is the thing that should be unitary if you've characterized everything perfectly and you've actually accounted for all your loss. So of course, V dagger should be the identity. But again, it wasn't, which again I was actually also pleased about. It tells me I can't do perfect measurements, which I like. These diagonal elements are just still 1 by construction, and anywhere where you see some intensity here in the V matrix is just where, in this VV dagger, it's telling you that how non-unitary your measurement was. So we just used this matrix to predict some simple quantum behavior just by putting 2 single photons into the into the circuit, where non-classical interference should occur, and then you detect the outputs with avalanche photodiodes. And the system works really well. As you can see, there's 15 different input configurations for 2 photons into a 6 by 6 circuit, and the classical characterization and the quantum measurements agree extremely well. So the take-home message of this characterization technique, importantly, it doesn't fully characterize the quantum behavior of the system. Okay, you need full process tomography to do that. But it is efficient. It scales polynomially with the size of the system. So the number of measurements that you need to do scales polynomially. That's important. And again, you don't need full process tomography for something like BosonSampling. But just some remarks about this as well. The old adage that there is a difference between knowledge and understanding. You can't gain any more knowledge about this device. You've characterized fully the beam splitter ratios and the phase shifts, the phase shifts inside the network. All reflectivities and phases are known, the loss has been characterized. It's a synchronized battery. There it goes. But understanding how quantum inputs are transformed requires something like boson sampling. And the difference there is the difference between classical and quantum computing power, essentially. I actually found this somewhere on the web. Even if you can explain it simply, you still won't understand it well enough. So, part 2 of my talk is this concept of trying to emulate quantum effects in biological systems. Again, I'm going to have to skip all the motivation for this because of time constraints. The team for this particular work was Devon Biggerstaff, who was leading the charge on this project. Myself, Alessandro Federici, is here in the audience. And we collaborated with Alexander Zamite, René and Marcus Graf from Jena. in Germany. They actually built the waveguide system that I'm about to show you. And Ivan Casal was the sort of brains behind this project. He's been working on these types of ideas for a long time. Aidan was on a student, obviously. This guy here was hanging around. The animals animals are interesting because they that's sort of threw me there. We already know in nature that animals use interesting physical properties to do all sorts of things. There's this fox that actually uses the Earth's magnetic field to bury itself into the snow to find rats and mice and things like that, and birds use a similar effect to navigate. The system we're interested in is the concept of enhanced energy transport in biological systems. In particular, we were interested in this light harvesting green bacteria that within it there's this FMO complex that's been studied to death by chemists and biologists that facilitates the transfer of energy from a light incident upon it. In a simplified model, this system is just a network of sites. Okay, so energy is incident on a couple of sites, and then transport occurs such that the energy can be trapped into a target site where it's converted into useful energy for the plant. One of the most important papers in this area for us was that by Robintrust et al., along with our resident theorist Ivan Casal, where they showed that in this system it's predicted that a small amount of dephasing in this network will enable enhanced energy transport throughout it. And this is this concept known as environmentally assisted quantum transport, or ENAQT for short. So typically you might think that noise would hinder the transport of energy across a lattice. For example, if you've got a fully coherent system, i.e. a quantum walk, then we know that the transport is ballistic in this system. If you add a lot of, if you add some dephasing, then you will get some diffusive behaviour, and even more dephasing will bring you to a Xeno regime. But the basic idea of ENAQT is that noise can bring detuned energy levels into resonance and facilitate transport across a network of sites. So, for example, in this toy model here, you start at an initial site on the left-hand side, and you want your energy to transport to a target site on the extreme other end of the network. If you introduce some noise and detune the level in between, it can temporarily bring those sites into resonance, and therefore you can facilitate transport across the network. So how do we emulate this problem in a photonic system? Well, what we used that Mike was talking about yesterday, although we didn't collaborate with him on this particular project, is these laser-written waveguide systems. So this is where they take a bulk piece of glass, shine a strong laser into it, and you can write these three-dimensional structures. So what you need for this particular simulation is to be able to, first of all, detune the energy of the sites themselves. So that's pretty simple in these systems. All you do is just detune the refractive index between neighbouring waveguides. Then you have to create this artificial trap where your energy, once it hits this trap, it just leaves and never comes back. So you can do that just by coupling one of your sites to a long string of equally spaced sites, all with the same on-site energy. So once your light hits those modes, it's gone forever. And also you need to be able to introduce some dephasing to show the enhanced transport in the system. And it turns out there's a really simple method to do it. All you do is just increase the excitation bandwidth. Since the different wavelengths will have different coupling constants depending on which waveguide they're in. So our model was extremely simple. It didn't look anything like the FMO complex that we would have loved to have simulated, but we're simulating essentially the effect of ENAQT, environmentally assisted transport. So it's a full site system with the trapping site here. So the trapping site in this case is site 3. And importantly, the site neighbour to it is this detuned site. Okay, so we start with an initial excitation in the first waveguide here, on the left-hand side. And the efficiency is how much energy is trapped in this site during the simulation time. And the introduction of dephasing will essentially detune this site. So the Hamiltonian of the system is pretty simple since it's only a 4x4. These betas, of course, are the on-site energies, the diagonals, and the C are the nearest neighbour coupling strengths. In our design, this delta beta in the fourth mode is equal to C. This sets up the system such that one of the eigenstates of the Hamiltonian is looks like this. And importantly, as you can see, this eigenstate has no coupling to the third site, which means that no energy can actually leak into the trap for that particular eigenstate. This means that the maximum coupling for this, the maximum coupling when you inject energy into the initial site will at most be 2/3 for the central wavelength that this chip was designed for. This is a little schematic that shows you essentially what the device looks like in real life. This Z here is essentially the simulation time. So the longer you make the chip, the longer you simulate the problem for. These strongly coupled sites on the right-hand side here are the trap, and the actual the 4 sites that I've shown up here are on the left-hand side. So we inject energy into mode 1 at the top here. The amount of light that's trapped in the trap over the simulation time changes as a function of wavelength. At the wavelength that we designed the chip for, it was pretty much exactly 2/3 as predicted. But as you increase the excitation wavelength, that's when you start to see the effect of environmentally assisted quantum transport. So we used a single photon source. We don't need to use a single photon source, but since we're good at making single photons in the QT lab, that's what we did. So we just used a short crystal to give us the difference in a large bandwidth of excitation. And as you increase the bandwidth of excitation, the amount of energy that's trapped in the site increases. So you can see that you've essentially provided evidence for this environmentally assisted process. So the take-home messages for this part of my talk is that we've demonstrated this very simple effect. It's a process that's believed to be behind some enhancements of energy transport in biological systems, which makes it of interest to us and to many other people in biology, for example. And I think a question is, are quantum effects playing a genuine role, for example, in the evolution of biological systems? I think these are, definitely some open questions. And Devin Bigstaff, lead author, just put the paper up on the archive last week. Oh, I haven't got the thing now, but if you're interested, come and grab me afterwards. Oh yes, so this brings me essentially to the end of my talk, where I have a small confession to make. Some of you may know that I'm no longer actually in quantum optics anymore. I've actually gone to the dark side. The dark side being silicon. So I made the transition about 1.5 years ago to work with Michelle Simmons at University of New South Wales. In that group, what we're looking at is these phosphorus atoms, single phosphorus atoms in silicon, essentially, where we have the ability to place single phosphorus atoms in proximity to one another, such that the extra electron that you get on that system you can use for a spin qubit. Okay. You just telling me to get in the camera, yeah? So as well as being able to place these single phosphorus atoms next to one another, we can also place other structures around. So we place gates and things to control the electrostatic environment of the system. That allows us to load electrons on and off. It allows us to do our spin readout mechanism. So those are supposed to be electrons. And go on, Barry.
You had your Broome and your reverse O'Brien.
Oh yeah.
Disappeared, but
So yeah, basically my transition from quantum optics to silicon has become known as the reverse O'Brien, because it's exactly what Jeremy O'Brien did, right? Someone asked me today whether I plan to go back into optics, but it's not known whether Broome dagger is equal to identity. It's
you might not be unitary.
Exactly.
Right. There's loss.
There's loss, exactly. I might have actually lost information, right, going to silicon. We had this discussion yesterday.
Yeah, I recall.
Exactly.
That was right before Keith stole the beard.
So, yeah, obviously you've got to be able to sense the charge that's on your, that are on your dots. So we use single electron transistors to do that. That modified our fabrication process over the last year to achieve that. I'm currently working on multi-electron structures and controllable interactions between them. And if you want to know more about that, then you come speak to me afterwards. So with that, that is the end of my talk. It's slightly shorter, I think, than I wanted it to be. But thank you for listening. The relevant paper's at the bottom here. And that's Jared Milburn in a cowboy hat, if you're interested. Thanks.
Now, actually, we have 10 minutes for a question.
Really?
If you want to talk.
So the environmentally assisted. So maybe you can answer the question. What's so it's quantum because it's a single photon. That
it's not quantum.
It's the bacteria in the bottom of the ocean, but it's only one single.
It's a wave effect. Yeah.
Even in the bacteria, like.
Huh?
Even in the photosynthetic complexes, is not.
Well, yeah, it would be. Yeah, I mean, if there's no like entanglement or anything, then it's not going to be quantum, right? That's I've started to develop this opinion that the single photon, single particle effects are just all not quantum.
Yeah. So
wave effects. Yeah.
So is your opinion or is also?
It's my opinion. It's my opinion. Yeah. I mean, yeah.
So it's not multi-photon.
Well, if it can be simulated classically, then it's a classical effect.
I mean, it's a single particle first order coherence.
Right.
That's it.
Yeah.
I can do it with water waves.
Yeah, you could do it with walk waves if you could engineer it in that fashion.
No, but okay, so I agree with that.
The reason they call it environmentally assisted quantum transport is just historical, I guess.
But from the chemistry, biochemistry,
but still a wave effect, even if it's an electron.
I still have the microphone. From the chemist, biochemist point of view, that they claimed this natural science papers, that there is quantum going on. We can kill it just to say it's a single photon, so no one.
Look, I mean, look, I think we're just talking about semantics here, but are you asking?
I think there was something more profound about the measurement that they could see in the biochemistry, not what we try to do as a
okay, so these measurements, right, where they excite these systems with lasers, and then some other people show that
I think it's still an open question.
Yeah, it's still an open question, yeah.
So we don't know the answer.
We don't fully know. We don't know. Yeah.
The way we treat it, I think, is classical.
Yes, indeed. Andrew?
So any plans to do, with your phosphorus and silicon, any plans to do the kind of Mick-Bremner type stuff?
So Andrew's referring to this work of Mick Bremner's where he shows an equivalent model for boson sampling for fermions, essentially. I mean, that would be brilliant. I think one great thing about being in Michelle's group is that we have the ability to place donors where we want to. And not only can we do that, but we can image them afterwards. It's great. I'm really looking forward to giving my first talk because, you know, can you show me a picture of the device? Yeah, it's there. You can see the atoms. You know, it's really quite brilliant. So, you know, that's a long-term goal. I mean, I guess it's equivalent to me asking you when you're going to do boson sampling with 20 photons.
Well, you might beat me.
Yeah, yeah. Should put a whiskey in it.
Your VV dagger wasn't quite one. Have you thought about or tried max entropy that or something of that nature?
No, we didn't really look into that. No.
Do you think that would help or work?
I think it would be interesting to see where that non-unitarity comes from. You know, is it some small non-linearity or something in your device that you haven't taken into account for in your model or something like that? You know, I guess the reason I said I was pleased about measuring it being non-unitary is because I don't want to be able to measure non-unitary things in the lab. Do you know what I mean?
Unitary.
So I don't want to be able to measure unitary things in the lab.
There we go, there we go.
Yeah.
Know what I mean? Yeah, no.
It's wrong.
Well, then it's sort of, you know it's going to be wrong because the universe won't allow you to measure unitary things. Yeah.
Can I just quickly expand on that question?
Austin? Barry?
So you have, you mentioned earlier, you went at the conundrum of how to know that what you measured was what you measured. You know, you said you're doing interference to characterize a device that you're using to do interference.
Right.
So you were painting a picture.
So I was painting a picture of, you know, if you wanted to do, you know, say you've got a system where you've got a black box and a classical computer scientist and a quantum computer scientist have access to it, right? The classical guy or girl can only have access to classical resources. So the methods where they use single photons to characterize their device and get the beam splitter ratios and phases, for me, well for us when we were doing our experiment, it just seemed a little bit circular.
So what's the solution?
Sorry?
So
what's the solution?
Yeah, fix it.
Is to use our method, right? Because it's efficient.
You mean the alphas in the Rahimi-Kashari alphas?
Yes, exactly, yeah.
You want to double dip?
Austin?
Not even.
No, I was going to actually, I was trying to interject before, but I was going to continue on from that previous question. I mean, how certain are you that this is a linear transformation of the field? Like,
well, yeah, I mean there will be some small non-linearity there. Right?
I'm trying to think if the Gaussian state characterization lets you see the non-linearity or not.
That would be interesting.
I think.
Well,
well, I'm saying is if there's like the tiniest level of non-linearity, but you assume your system is linear and characterize it in this way. Yeah, I'm not even 10 to the minus 20. Really?
But
he's not putting 3 gigawatts.
What does that have to be gigawatts?
it doesn't, but it's some.
It's got to be a
No,
but that's the point, right? It won't be 0.
Yeah, that's what I'm trying to say.
That's what Austin's getting at.
It's miles below what you're saying.
But it probably is, but Austin's making a principle argument. Right?
People who make fiber optic gyros have now reached the point that they're single photons per coherence length because any higher than that, the nonlinearity destroys their precision.
Yeah, because they're at the level of 10 to the minus 7 radian precision.
Right. Well, so that's the whole point. I mean, so there is a point where the nonlinearity matters.
Right.
And you have to be gigawatts.
Matt's maybe got 100 or 200 points across his fringes.
Okay, fair enough. He's not going to see them in this system.